We have used scattering experiments to study the finest details of our universe, dating back to 1906, when Ernest Rutherford conducted his alpha particle scattering experiment, which led to the discovery of structure of atom. Today, we have experiments like the Large Hadron Collider, which is probing into structures much finer than the atom. Over the years, there has been one major shift in the type of scattering experiments we do. We shifted from having an accelerated beam of particles striking a stationary target to having two accelerating beams of particles colliding at the center. The former is called a fixed target experiment and the latter is called a collider experiment. I would have to clarify that we still use fixed target experiment for various studies, but from a particle physics point of view, the focus is clearly been on the collider experiments. There are many benefits for the scheme, but the main reason for that shift is energy. In order to probe the finer details and to search for rare processes and particles, we need more energy at the point of collision. If you think whether it is worth the difficulty in establishing such high energy colliding beams to just have twice the energy, let's look at some maths. Trust me, it's not difficult, so stay with me. If we solve for energy momentum conservation for a relativistic two-body collision, we get this relation. Here the MCOM is the mass at the center of mass, which signifies the highest mass of a particle that can be created as a result of this collision. I like to express this equation in this form, which makes understanding a bit easier. As you can see, all the terms are now in terms or in the units of energy squared. Now, if we look at the collider experiments with identical particles with same energy and momentum from opposite directions, like in the case of LHC, we have the momentum vectors P1 equal to minus P2. Then we can simplify it to this equation. Now, the kinetic energy of particles in LHC are much higher than the energy equivalent of their masses, mc square. The kinetic energy of protons at LHC is 7.8 tera electron volt, while their masses only account for 0.938 giga electron volt. So the kinetic energy is roughly 8,000 times their mass equivalent. So we can use this relativistic approximation and we neglect the terms which only have mass and the quantity momentum times c, the speed of light, would be roughly equal to the total energy E. So now simplifying the equation, we get the center of mass energy as twice the individual beam energy, which probably you expected. Also, particle physicists usually use what is called natural units to write equations, where they take the fundamental quantities like the speed of light in vacuum and reduced Planck's constant as dimensionless numbers equal to 1. So we can represent mass in the same units as energy. Here I am just showing both the notations, don't be confused. Now let's do the same calculation for the fixed target scattering. Here one of the momentum, say P2, will be 0 as it is a stationary. So this term vanishes and the energy of the stationary particle would just be its mass energy. So doing identical calculations we get this result for the center of mass energy. As you might have already noticed, the accessible energy at the point of collision is not the arithmetic sum of the energies of the colliding particles, but it is closer to their geometric mean. If we put this in LHC numbers, we can see that the center of mass energy for the colliders is more than 100 times larger than that of a fixed target experiment. This is because in such a symmetrical collisions, the particles get stopped and their whole momentum and energy is available for production of new particles at the center. But in the case of fixed target scattering, the scattered particles carry away most of their energy after collision. So with these colliders, we can generate particles as much as 100 times as heavier than those we could have produced otherwise. And that is why we use colliders over fixed target experiments. So if you found this video useful, please subscribe to the channel and see you with more content like this.